So here's going to be my example. I'm going to have a diving board. So if you've ever had a diving board, you know those springy ones, right? You can jump up and down at the end, and they kind of can shoot you up into the air. Let's say that someone is contemplating a jump. Okay, they're not in the act of springing, just kind of hanging out, staring at the water. We want to look at a system where there's nothing happening. Okay, we want to make this a static equilibrium system, so they're not in the act of jumping. Now, if you want the diving board to be springy, okay, you do not want to put a support anywhere near that. So here's my diving board in person system. So I have the person that's going to be this thingy here on the end, this clamp, and then this is going to be the diving board. Now, by the balance method, we know that if we want the system to stay balanced with a single support force, we have to put it somewhere pretty close to here, right? But that's not going to let the diving board be springy, so let's not do that. In fact, what I'm going to do is I'm going to have the givens are that the mass of the person is going to be 50 kilograms. Let me just double check, that's my number. Yep, 50 kilograms. And I'm going to actually have that the diving board is relatively massless in comparison, so I'm going to neglect that. Not that it's really hard to include. I'll say a few brief words on what you would do if you had to consider it. But in this odd system where this diving board has no mass, therefore would levitate on its own, right, because it has no gravitational pull, if I wanted to hold this system up, I would have to put my force here, right, because all the mass is over here. And then the support would be right under them, and then they couldn't spring off it. So that's the downside of the single support, right? If you have a single support, you have to put it at the center of mass. Well, guess what? I can hold this system up without putting anything at the center of mass. I do it like this. I have one force up over here, but I have another force that's down, like this. So it's totally possible to hold something up, not anywhere close to the center of mass, but again, you have to use more than one support force. A single support force needs to be put at the center of mass, but if you are willing to use two forces or more, and you're willing to vary their direction, notice how far away both of these are from the other end, right? So what I do is I exert one force, like this, and then of course if it was just this one force, it would flop over like this. And so the other force is actually having to hold this end down so it doesn't flip up, right? So I have two forces like this, and that's exactly how the diving board is going to get held up. So this, I'll call the length of the diving board 5 meters, and I'm going to have two forces of support like this, and one is at the very end, and one is only 2 meters from the end. I'll call them supports A and B. There's my system. So it's possible to hold up a diving board. Even though all the mass is on the right, I have two supports which are to the left of the middle. Okay? Now, diving boards don't really have a claw that hooks over the top of the end like that, but that is the job of that support at the end. The job of the support at the end, A here as I've labeled it, is not to hold the diving board up. That's the job of B. The job of A is when a person is sitting or jumping up and down on the right end, it keeps the left end from flipping up into the sky, right? So the job of this support is to hold the end down. So here is going to be my question. What is the support force supplied from each thing? And by the way, it is a normal force because I'm using for my support forces two solid surfaces that don't want to get smushed. So some kind of solid support. So that's my setup. These are the, this is the location of the mass. Is the person on the On the end, I have a 5-meter long diving board. I have 2 supports. One is at the left end, one is 2 meters in. And I want to know how much force they each have to hold up. So, let's go through our problem-solving strategy. Step 1, identify the rotational system, the object or group of objects that rotate together. So if this person is firmly seated on the diving board, either the diving board and the person are going to either stay there, or if there's some kind of catastrophic collapse, both the board and the person are going to fall up together. So I'm treating this guy and the board as one. That's my system. They move together. In every problem, you're going to identify a group of objects that you're basically going to treat together. They're your rotational system. Now, step 2, I want to identify external forces that act on it. This is key. Only external forces. Not internal forces, only external. And I want to make sure to put them at the right places. So, can anyone name a force that acts on this system overall? Gravity. Gravity. Where should I put it? Where the person is. That's where all the mass is, right? What might you do if the board itself had mass?
On the center of mass between the person and the board.
And then have all the weight act there? Yeah, you could do that. That would be an extra calculation to do. Another way you could do it is just to take a second force of gravity. So count the force of gravity separately on the 2, right? Where might you take that force for if it's a uniform board? In the middle. So you have a second force of gravity here, right? No big deal. It just adds an extra annoying force that I don't want to deal with right now. It doesn't substantively change the approach at all. So, could you find the center of mass of the 2 and take the entire force of gravity there, both of their masses times g? Yes, but that'd be an extra step. It's a lot easier to have your cake and eat it too. So even though you're thinking of them as 1, for the purposes of force of gravity, you'll say, I'm going to take it as 2. Okay? So I think you do have some problems on your homework and or practice exams like that, but that's really not a substantive change to the problem. So for my purposes, the diving board has negligible mass, therefore all of the weight is acting at the person. Okay, what's another force that comes in from outside of the system?
Normal force.
Normal force.
A and B.
A and B. We've already said that the normal force on B holds up the system, and A keeps the end from flipping down, or flipping up. Any others? Any ideas? Any other forces coming in from outside? Nope. There aren't. So, good. This is where students start including extra forces that aren't relevant. Common mistake is to include, and it might say, isn't there a normal force on the person from the board? Doesn't the board hold them up? Sure. That's true, but it's inside, right? It's inside the system. You don't care about the person acting on the board or the board acting on the person. That's inside the system. Something from inside the system could never just pick up the whole system and rotate it one way or the other, right? Or cause it to move up or down. Forces from inside is what could, like, for instance, repel two parts of the system from each other or attract them or something like that. We don't include those. We only include forces from outside. So that's where things can go wrong in the first place. I'd say step 2 is where a lot of stuff goes wrong because you can either include too few forces or too many. Okay, and again, you want to include only external forces. Don't include anything that acts on one part of the system from another part of the system. And the other thing, of course, that can go wrong is that you get the force in the wrong place. It's important, where does it act? Okay, so these forces are all in the right places as well. Okay, so once we've got that all set up, let's go ahead and write down, let's do the force equations first. So let's, I guess, take this way to be the plus y direction. So F net y equals 0. And I have three competitors. One normal force acts up, and then one normal force and the force of gravity acts down. And solving, this is something you maybe could have written down to start with. The out force is equal in size to the two down forces. So hopefully that part's old hat. And of course, there's no reason whatsoever to write down an x equation because absolutely nothing is going on horizontally, right? There's no forces acting at all in that way. So this is a perfectly fine equation, but it just gives me a relationship between the two normal forces, both of which are unknowns. So no matter how hard you try, you hopefully know that mathematically speaking, it's impossible to solve for both of these. You can't get two unknowns out of one equation. The best you can do is to put down mg. Mg, if you multiply the mass that I gave you, 50 kilograms times g, you get 490. So the only thing that tells you is that the normal force B is greater than normal force A by 490 newtons. But of course, there's an infinite set of numbers that would satisfy that equation. Only thing you have to make sure, pick your favorite number for NA, and NB is 490 more than that, right? So, of course, that's because there's more to this. Not only does the net force have to be 0, the net torque has to be 0 as well. Okay? So that's where we're going to get our second equation. And with two equations, we can solve for two unknowns. Okay? So this often happens, of course, is that you're not lucky enough that one of your things that you want falls out of this and one of the things you want falls out of this equation. They're intertwined, and you got to do a little algebra to get them both, right? So, are there any questions on that before I move on to the torque equation? Okay, so let's do that. We have a little space here. So let me make kind of a free body diagram here. Might make my life easier to kind of take out some of the details and draw in these three forces. That's my rotational system. Those are the three forces that act on it and the correct locations. Now this is a problem where, unlike the seesaw example we did last time, there's no obvious pivot to use, right? A seesaw has a pivot because a seesaw is meant to rotate. This system, not so much. So if this person is just sitting here, so here again, here's my system, how is it going to rotate with the person sitting on there? Well, it's not going to rotate at all, unless there's some kind of catastrophic collapse, right? Someone didn't build the diving board right. Maybe this support gives out, support A. Then it's going to go like this. It's going to rotate around B, right? If support A gives out, B is left, and it rotates around that. Or maybe support B gives out. Maybe that collapses, and then it's going to rotate around A, right? You don't know. You don't have a crystal ball. You hope that this thing never collapses. So this is where we just pick a pivot and go with it. So here's where we have to talk about how you might pick a pivot. So if there is no actual rotation, you can pick whatever pivot you want. It's purely hypothetical, okay? Whatever you pivot you pick, you better get the net torque to 0. Because this thing is not actually rotating. So whatever pivot you pick, you better find that the things trying to rotate it clockwise around that pivot are balanced by things trying to rotate it clockwise or counterclockwise. I forget which one I said first, right? The net, think about how weird that would be. If you pick one pivot and you got the net torque with 0, that means it's not spinning. What if you picked another pivot and you didn't get the net torque with 0? then it means it is spinning. Well, how could it be doing both things at once, right? It's not spinning. And if it's not spinning, that means the net torque has to be 0 around any pivot, right? So you can pick whatever pivot you want, and knowing that the net torque should be 0 around that because it's not actually spinning. So that seems great, right? You can't go wrong. Picking a pivot, any pivot you could draw out of a hat, the net torque is 0 around that pivot because it's not actually spinning. But then you're kind of spoiled for choice. You might say, well, if I can pick anything, what do I pick? So then there's an art to making your life easier instead of harder. So let me give you some tips for choosing wisely. This is just for the purpose of making your calculation shorter instead of longer. The net torque will be 0 on any pivot, but some of them you might be at it all day, and other ones you're out of there in a few minutes. So it's not that in this problem that I'm working on currently, I'm going to have some totally disastrous choices and totally awesome choices. The problem is not that complicated. And so let me, to try to emphasize my point, try to pick some really crazy extreme examples, okay? So let's say, for instance, I had a force configuration that looked like this. Now obviously I'm picking an extreme number of forces on one side, and I'm doing this to make a point. Let me take a look at potential pivot choices and see how they might be good or bad. The one pivot choice that I think students want to make a lot is to pick the middle, right? It's somehow sensible for the pivot to be at the middle. A lot of times that's where the center of mass is, so that's a very natural pivot, right? We know that when things actually rotate, they often rotate about the center of mass. Not always, sometimes you can force them to rotate in other ways. And if something actually is rotating, you do need to use the actual pivot. But it's also easy to find. The pivot's what everything else is going around. But if you pick the middle here, how many forces do you have that have leverage against that pivot? How many forces act somewhere else besides that point? 8. You have 8 torques to compute. Pivot choice A will give you 8 torques. Because you have 8 forces that have leverage against that pivot. Let's take a look at some other choices. Let's take a look at B. B is at the left end. So I'm going to pretend the hinge is there. And one of those forces is acting at the hinge. What happens when you try to open a door by pushing on the hinges? Nothing. How much torque does this force exert? 0. I'm not saying the force is 0. I'm saying it does not exert any torque, right? Because it acts at the hinge. I'm pretending that B is the hinge, and one of the forces acts there. So I immediately know that that torque is 0. How many other torques am I going to have to mess with? 7. 7 torques. 7 is better than 8. What if I pick the pivot choice at this force? How many torques would I have then? 7. Again, 7. You can see hopefully where I'm going with this. What if I pick the pivot at D? How many torques do I have to do? 2. Because 6 of the forces act at the hinge that I'm pretending is there. And if you have 6 people pushing on the hinges of a door, it will not open. So would you rather compute 8 torques or 2 torques? I would rather do 2 torques. Okay? So this is the winner. If you can pick whatever hinge you want, let's pick a hinge where at least we can throw away at least one force. So going over into my problem, I really only should consider 3 hinges. This one, or this one, or this one. I should not pick the middle of the diving board, because in the middle of the diving board, none of the forces act there, and I have 3 torques to contend with. If I pick one of those 3 pivots, how many torques am I going to have to mess with? 2. Only 2. All right? So that's one consideration. for making your life easier by picking a pivot choice wisely. I'll give you a second and final tip for doing that. Here's a situation, and it's much like ours. Let's say 1, 2, 3, like that. There are 3 forces that act like so. The first tip has already taught us that we would only want to consider 3 possible pivots. I guess I'll label them here A, B, and C. Those are the only pivots that we want to consider. What might make one of those better than another? Well, forces can fall into different categories. Just like we've talked about throughout the class, there are 3 different classes of variables. We have the know it, it's given. We have a want to know it, which we mark with a question mark. And we have a don't know, don't care. Right? Those are the classes of variables that we have. Things we know, things we want to know, and things that we don't know and don't care about, but which may creep into the problem, of course, because even though it's not mentioned in the phrasing of the question, even though it's not given or asked, you should never hesitate to introduce something if it's relevant to the problem, right? If there's something going on, you can't just ignore it because it's not in the paragraph, right? So let's take a look at choices A, B, and C here and get a little flavor of what appears. Now, if I pick pivot choice A, this force, which we know, its torque will be 0. So that won't even appear. The 2 things that will appear are the 2 forces that have leverage with respect to the pivot, which is the want to know it and don't care. Right? Now let's take a look at pivot choice B. Pivot choice B, the force we want to know exerts no torque against that hinge. So the things that will appear are the thing we know and the thing we don't want to know. And then finally, pivot choice C, the force we don't know and don't care about is not going to appear because it acts at the hinge, so we're going to have the thing we know and the thing we want. So which one should we use? C. It's a great way to get around forces that you could give less of a crap about is by putting the pivot there, so then they won't even appear in your torque equation. That's great. It's a way to get around not having to worry about it. Okay? So if I were to summarize my advice for picking a pivot wisely, I'd say pick it to be where there's a large number of forces and or unknown that don't care about forces. So pick the pivot such as you can minimize the number of torques involved and minimize the number of unknown and unwanted forces in your calculations. So that, if we go back to our example at hand, of course, if I were only asking you for NB, right, then the pivot choice is a no-brainer. What would I pick? This one, right? If I only wanted to know NB and I didn't want to mess with NA at all, I'd pick the pivot here. Likewise, if I only wanted to ask you for NA and you could don't know, don't care NB, pick the pivot there. Now, in my case, of course, I asked for both of them, right? So you're going to have to come around and get the other one. But I will warn you off one of the pivots. This one. Is it wrong? No. Is it going to make your life more difficult? Yes. Here's why. If you pick the pivot here, then these 2 forces have leverage against that pivot, and both of those forces are going to appear in your equation. You'll have a second equation with NA and NB in it, and you'd have to solve it with this one, and it's going to be annoying. You'd have to do your 2 equations, 2 unknowns math. You know that's annoying. You just, like for instance, your 2-dimensional collision problem that everyone hated, right? Remember that? Having both unknowns in both equations is just a little annoying. I'm going to suggest, let's pick this to be the pivot, because then NB is going to pop right out. It's going to pop out, and we're going to get the number, And then NA is really easy to get because I just get it from here. So let's go ahead and work that out. Let me go over here. I'm going to need to clear a little space. So here's my free body diagram. And in this case, just to kind of make things clear, I'm going to mark the pivot, and I'm only going to include the forces that have leverage against it. I'm not including the force of A because force of A pulls against my hypothetical hinge. So here's what I'm basically pretending. I'm pretending that the pivot is here, okay? And what we have is one force, the force of gravity, which tries to rotate the system like this, right? That rotates it from your perspective. I have to reverse everything. That's clockwise for you guys, right? Now, it's not actually going clockwise. It's because the other force wants to rotate it like this, right? So that one would want to rotate it counterclockwise. So what we are pretending, basically, is that this is my hypothetical pivot. This force tries to get it to go this way. The other one tries to get it to go that way. And if they cancel each other out, there is no actual rotation. So let me draw that. So you draw that force around the pivot. Make sure you go around the pivot. Right? My hypothetical pivot is there on the left end. This torque is going to be plus. Torque of B is plus, or counterclockwise. The torque of gravity, let me draw that. Now, I see this all the time, and I'm not sure where this is coming from. Students will go like this. Where are you going? Okay? That's not, the pivot is over here, so I want to draw around the pivot. I'm not going to draw the whole thing, but make sure you're making a circle around the pivot that you've chosen. So this is the torque of gravity, and that's going to be negative, or clockwise. You can do a head check at this point and say, you better get a mix of plus and minus torques, because your net torque is supposed to be 0. So if all your torques are clockwise or counterclockwise, then it can't possibly be 0. Okay? So here's what we do. We now say that the net torque, which is the torque of A plus B plus G, has to equal 0. And because of our pivot choice, A went to 0 immediately. It has no leverage. That's why it's not even included in the diagram. So what we're going to have to make sure is that these two torques kill each other. The torque of B and torque of G are going to balance each other out. So let's work out the details. Remember my torque formula? It's plus or minus for the direction, and then RF sine theta. If I want to know how much torque I get, it's leverage, force, and orientation. RF and theta all matter. Let's quickly get the theta. The theta, remember how you get that? You draw a dotted line from the pivot through the force application point. Kill two birds with one stone on this one, because the same radial line will go through both force application points. And then I measure the angle between them, which is 90, right? So the radial line makes a 90-degree angle with both forces. Sine of 90 is what? 1. So my torques will just be R times F. Haven't diluted the amount of force available. In fact, both of these forces are perfectly tangential, right? All of the force is relevant to rotation. All right, so let's put it in. We decided that torque was positive. We decided that the other one was negative. And they have to cancel. All right. So let me write it like this. that basically says the torques have to have the same size. One is one way, one is the other way, but they have to have the same size. Now, this is again where we get to the seesaw example, right? We said that there's no way you can seesaw with a little kid if your forces have to be equal. You weigh more than a little kid, it's just a fact. But the torques have to balance in a system, right? So if you want to seesaw with a little kid and you have more force of gravity acting on you, you have to make it up for with less leverage, right? So you sit closer. So that's what we have here. It's not quite a seesaw. Both of the forces are actually on the same side, but the forces are in opposite directions. Now, which force has more leverage against this pivot?
G.
Gravity. So this has more leverage, so what does that mean about the force if these are going to cancel?
Bigger.
Bigger? They're both bigger? Smaller, that's right. Likewise, since the leverage of B is so much smaller, the force has to be larger. So our prediction here is that the force of B is going to be larger. If you need evidence of this, think about it like this. If I have to take this gravitational torque, and this has a lot of leverage, force is acting all the way over here, here's the pivot, it acts all the way over here, and I want to cancel it off with something that has very, very little leverage. I'm going to have to push a lot harder. Right? I have to push a lot harder here to hold this up. Okay? So, let's work out the number. I guess I should call this NB because it's a normal force. I should call this mg because it's a gravitational force. Now we have to work out the leverages. So NB, if I solve, is going to be like so. How much leverage does the force of gravity have as a number? How far is it from the pivot? 5 meters. This is 5 meters away. How much leverage does the other force have? 2 meters. So notice that everything flows from the pivot. Once you've chosen the pivot, first of all, when I chose the pivot, one of the torques was 0. Then I looked and I saw that the two other torques, one was plus and one was minus, that flowed from the pivot. And how far you are from the pivot depends on where you pick the pivot. So because I picked the pivot on the left, the two forces have leverages of 2 meters and 5 meters respectively. So we put that in. Remember that mg itself was 490 newtons. And if we put in 5 and 2, we'll get that this force is 1225 newtons. Which, of course, is indeed greater. So if we go back over here and we catalog the forces, this is 490 newtons, but this is 1225 newtons. Okay. So how might we get the third force now, the NA? Throw it in here. Classic two equation unknowns, right? Because of my wise choice in pivot, NB just popped right out. And then I throw it in here, and I get that NA is 735. So if NB is 1225, this is 735. 735 newtons. Okay? These are my three forces. Notice that I have been able to exactly find the 1225 newtons and 735. There can be no other values of these two forces. Now you might say, is it really exactly have to be those? If I take away a newton from this one, and I take away a newton from this one, do the forces still balance up and down? If I take a newton from here and a newton from here, the forces up and down are still balanced. But over here, the torques won't balance, because now this force doesn't have enough torque to cancel this one, right? So only these two amounts are possible. As a closing note, I would recommend that you work through the problem But instead of picking the pivot to be at A, pick it at B. So then the diagram would look like this. Then the torque of B is 0. Everything flows from the pivot, right? Now I'm taking the pivot at B, so that does not exert any torque. Now this torque is no longer 0. It is positive or counterclockwise. This one is still negative, but even the leverages change. How much leverage does this force have? 2 meters. How much does the force of gravity have? 3, right? Notice that the leverage depends on the pivot choice. If you do it that way, you should be able to get NA popping out to be 735. And then you plug it in here and you'll get NB is 1225. All of these you can do a bunch of different ways to get practice and make sure you always get the same answers. Okay, that's it for static equilibrium. Do more on Monday.